Welcome to G Fun Facts Online. Today, we are hunting a ghost. Not a supernatural one, but a ghost that haunts the very equations of our universe. We are talking about the graviton. This is the hypothetical particle that carries the force of gravity, just as the photon carries light. For nearly a century, finding the graviton has been considered the ultimate prize in physics, but also the ultimate impossibility. Today, we are going to explore why that narrative is shattering and how humanity is currently building the machines to catch this ghost. To understand the stakes, we have to look at the two kingdoms of modern physics. On one side, you have quantum mechanics. This is the rulebook for the very small. In this world, everything is pixelated. Energy comes in chunks, or quanta. Light isn't just a wave, it's a stream of photons. On the other side, you have general relativity, Einstein's masterpiece. This describes the universe on the grandest scales. In Einstein's view, gravity isn't a force carried by particles. It is the curvature of space-time itself, a smooth, continuous fabric. The problem is that these two theories hate each other. They are mathematically incompatible. When you try to combine the pixelated world of quantum mechanics with the smooth fabric of general relativity, the math breaks down and gives you nonsense answers like infinity. The graviton is the peace treaty. It is the proposed quantum of the gravitational field. If we can detect one, it proves that spacetime isn't smooth at all, but is made of a swarm of tiny particles, just as the smooth pressure of a gas is actually the chaotic motion of billions of atoms. Theorists know what a graviton should look like. It must be massless, it must travel at the speed of light, and it must have a spin of 2, which is unique among all particles. But its defining characteristic is its weakness. Gravity is roughly 10 to the power of 36 times weaker than electromagnetism. A simple fridge magnet can lift a paperclip against the entire gravitational pull of the Earth. This extreme weakness is why the graviton was deemed undetectable. This brings us to the Dyson limit. In the early 21st century, the legendary physicist Freeman Dyson did a back-of-the-envelope calculation that cast a long shadow over the field. He imagined a detector designed to catch a single graviton through thermal absorption, similar to how a solar panel absorbs light. Dyson calculated that because gravity is so weak, the probability of an atom absorbing a graviton is vanishingly small. To detect just one, you would need a detector with the mass of the Earth. But if you built a detector that heavy, its own gravity would collapse it into a black hole before you could finish the experiment. Dyson concluded that detecting a graviton was physically impossible. He estimated that even with an Earth-sized detector orbiting the Sun, we might see only 4 events in the 5 billion-year lifetime of the Sun. For years, this was the end of the story. But physics is the art of finding loopholes. Dyson's calculation assumed we were looking for thermal gravitons, the faint, steady trickle from sources like the Sun. But in 2015, LIGO detected gravitational waves, ripples in spacetime, caused by colliding black holes. These aren't faint trickles, they are tsunamis. They are coherent states, consisting of massive numbers of gravitons acting in unison. This changed the question. We don't need to catch a whisper. We need to hear the individual clicks inside a roar. This is where the revolution of quantum sensing comes in. We are now using the fragility of quantum systems to measure the world. In August 2024, a team led by Igor Pekovsky proposed a way to beat the Dyson limit, using something called the gravito-phononic effect. Here is how it works. Instead of an Earth-sized detector, imagine a massive cylinder of aluminum or beryllium, weighing perhaps a ton. This cylinder acts like a bell. When a gravitational wave hits it, the bell rings. In our classical world, that ringing is smooth. But in the quantum world, vibration is pixelated. The unit of vibration is called a phonon. The proposal is that a single graviton from a passing wave can hit this massive bar and be converted into a single phonon. It is a direct energy transfer, graviton in, phonon out. If you can monitor the energy level of the bar with perfect precision, you would see the energy jump up in a discrete step. That step is the signature of the graviton. To do this, the engineering requirements are staggering. First, you have to cool this 1-ton bar to its quantum ground state. You have to remove all thermal energy until it is effectively at absolute zero. If there is any heat, the bar will be vibrating already, and you will never see the tiny kick of the graviton. Once it is cold, you face the second challenge, Heisenberg's uncertainty principle. You cannot just touch the bar to measure it, because the act of measuring adds noise. The solution is a technique called continuous quantum non-demolition measurement. Instead of measuring the position of the atoms, you measure the number of phonons directly. You couple the massive bar to a tiny superconducting qubit, similar to the ones used in quantum computers. When the bar's energy jumps up by 1 phonon, it shifts the frequency of the qubit. By watching the qubit, you can see the jump without destroying the delicate quantum state of the bar. The team calculated that with this setup, we wouldn't need to wait a billion years. We could detect single graviton events from a neutron star merger in a matter of minutes. If we succeed, the implications are profound. First, it kills the idea that gravity is a classical background field. It proves gravity is quantum. Second, it allows us to test the interface of reality. Sir Roger Penrose has proposed that gravity is responsible for the collapse of the wave function, the reason we don't see Schrödinger's cats in real life. A graviton detector would be the perfect testbed for this theory. We could finally understand why the quantum world becomes the classical world. The road ahead is difficult. The enemy is noise. Cosmic rays, seismic vibrations, and thermal heat all conspire to mask the signal. We will likely need to build these detectors deep underground, suspended on isolation systems better than anything currently in existence. But we are moving from philosophy to engineering. We are building the traps, quieting the noise, and cooling the atoms. Soon, in the deep silence of a cryostat, a single quantum of spacetime will ring a bell, and the unfinished symphony of physics will finally be complete. Thanks for listening to G Fun Facts Online.